Hello everyone, welcome to part 2 of You Could Have Invented Homology. In this video, we're going to start building our collection of topological spaces. But first I wanted to say, the reception to my last video was really amazing. I didn't expect to get such a show of support. I love making these videos and I'm so happy to see that you all seem to love watching them. In some news, in the time since my last video, something amazing happened. I got accepted into my dream PhD program. I start in April, and unfortunately this means that come April, I'll have a lot less free time to make videos. I'd love to keep going and maybe even make some videos on my research, but I can't make any promises at this stage. I'll do my best to finish this series before then. In the meantime, please consider supporting the channel on Patreon at patreon.com/Boarbarktree. Finally, for the many of you who have understandably asked, the software I use to make these videos is Adobe Animate, and I use a Wacom tablet to do the drawing. Alright, on with the show! The first topological spaces we'll meet are the most important of all topological spaces, the so-called Euclidean spaces. For each natural number n, let Rn denote the set of all ordered lists of real numbers of length n. If n is 1, this is the same as the set of real numbers. If n is 2, then elements of R2 are ordered pairs of real numbers. We can think of these numbers as being coordinates relative to a pair of coordinate axes. As Descartes realized, points on a plane correspond one-to-one with pairs of coordinates relative to some fixed axes, so R2 is a plane. Similarly, if n is 3, we get a three-dimensional space where points are defined by coordinates relative to 3 axes. The same is true for n equal to 4 or more. Points of Rn live in an n-dimensional space where they're defined by their position relative to n axes. Rn carries a natural notion of continuity, a topology, and Rn together with this topology is called Euclidean space of dimension n, or Euclidean n-space. The Euclidean spaces are the perfect topological spaces. You may not like it, but this is what peak performance looks like. Mathematicians like Rn so much that much of modern mathematics can be accurately described as just comparing various things to Rn in various ways. Rn is a perfectly uniform, featureless blank void. It has no holes and no handles, no surprises and no disappointments. We'll see later that the homology of Rn is 0, and homology isn't even a number. Rn is our reference point for having absolutely nothing going on, and that's why we love it. In addition to acting as a reference for the ideal topological space, Rn serves another purpose in topology. It's a source of new topological spaces. Because Rn carries a notion of continuity, any subset of Rn inherits a notion of continuity. There are some subtleties here that I'm going to brush over, but the continuity on Rn still makes sense if we restrict it to a subset. So we can take Rn and throw away some or even most of its points, and what we're left with is a topological space in its own right. This construction gives us many topological spaces. One way that we can use this to produce new, interesting topological spaces is with equations. For instance, if we take the set of points xy in R2 such that x squared plus y squared is 1, then, by Pythagoras' theorem, we get a circle. We can also use inequalities. For instance, the set of points xy in R2 such that x squared plus y squared is less than or equal to 1 is a filled-in circle, or a disk. Pretty much all of the topological spaces that are going to show up in these videos are going to be subsets or at least homeomorphic to subsets of Rn for some n. Why? Well, first of all, everything else is weird, like incomprehensible. There's already plenty of weirdness that goes on inside Euclidean space. We can do a ton of interesting and important mathematics without thinking about things like the Sorgenfrey plane or the long line. Second, I could never hope to draw you an accurate picture of anything other than a subset of Rn. And even then there's no guarantee, since, after all, the screen you're looking at is basically just a pixelated version of a region of R2. Even any 3D looking things are just projections. So, we're stuck with Rn, but that's fine. Now, as I said in the last video, the first thing we need on our journey into algebraic topology is some simple spaces. Now we've got our home base Rn, and directions for how to get to more exotic places. But it's a big world out there, so let's start with the true basics. Think of the simplest geometric figure you can. The kind of thing that they taught you to identify in primary school. You're probably thinking of some kind of polyhedron. Simplest among these is a triangle. Perfect. Even simpler still are line segments, and the simplest space of all is just an individual point. A surprising fact about these three shapes is that they're actually closely related. There's a formula that defines all three of them. Consider the line segment. It consists of all the points between its two endpoints. That is, you can get to any point on the line segment by starting at one endpoint and walking towards the other. If we think of these points as elements of R2, and we call the endpoints x and y respectively, this amounts to taking the vector x and adding to it scaled copies of the vector y minus x. So the points on the line segment are those that can be written as x plus t times y minus x, where t is some real number between 0 and 1, inclusive. Rearranging, the line segment is those points 1 minus tx plus ty. Notice that the coefficients here, t and 1 minus t, are both between 0 and 1 since t is, and their sum is t plus 1 minus t equals 1. In fact, if you add any number s to t and get 1, then s must be 1 minus t. So you could also say that the line segment is the set of points of the form sx plus ty, where s and t are between 0 and 1 and add to 1. Now consider a filled-in triangle. This space consists of the line segments between points on its boundary. That is, given some point, you can get to it by first walking from vertices along the line segments that form the boundary, and then walking along the line segment between those 2 points. So, as before, any point arises as 1 minus tx plus ty, where x and y are points on the boundary. But x and y lie on the line segments between the vertices of the triangle, so they themselves are of the form 1 minus SV1 plus SV3 and 1 minus RV2 plus RV3, where V1, V2, and V3 are the vertices. Simplifying, this gives the following. Now, this is not so nice to look at, but there are a few important things we can learn by doing this. First of all, our point is a sum of scaled copies of the vertices, just like how a point in a line segment is a sum of scaled copies of the endpoints. Let's take a closer look at the coefficients in this sum. Since r, s, and t are all between 0 and 1, 1 minus r, 1 minus s, and 1 minus t are as well. The product of any two numbers between 0 and 1 is, again, between 0 and 1. this implies that the first two coefficients, namely 1 minus t times 1 minus s and t times 1 minus r, are between 0 and 1. As for the last coefficient, notice that this is of the form 1 minus t times something plus t times something else. So it lies on the line segment in R1 between the numbers s and r. Since s and r are between 0 and 1, this implies that our third coefficient is between 0 and 1. So our point can be written as a sum of scaled copies of the vertices. What's more, all the coefficients are between 0 and 1, and they sum to 1. Watch. So, every point in the triangle is of the form t1v1 plus t2v2 plus t2v3, where the ti are between 0 and 1, and they add to 1. It's a natural follow-up question, then, to ask if the reverse is true. That is every point of this form a point of the triangle? Could it be the case that whenever you scale the vertices as vectors by numbers between 0 and 1, which add to 1, then add those vectors together, you necessarily end up in the triangle? Delightfully, this turns out to be true. Let's prove it. But first, I'm spending a lot of time saying the sentence scaled sum with coefficients blah blah over and over, and that's a problem that's only going to get worse. So it's about time we introduce some terminology. Definition. If X is some set of vectors, such as, for instance, the set of vertices of a triangle, then any vector which can be written as a sum of scaled copies of vectors in the set X where the coefficients are between 0 and 1 and add to 1 is called a convex combination in X. Why convex combinations? We'll get to that in a moment. First, let's prove our result. So, we've shown that every point in the triangle is a convex combination of the vertices of that triangle. Now our goal is to prove that any convex combination of the vertices is a point of the triangle. So, let X be an arbitrary convex combination of v1, v2, and v3. That is, suppose that we have numbers t1, t2, and t3 between 0 and 1, which add to 1, and consider the vector x equal to t1v1 plus t2v2 plus t3v3. If any of the ti are 0, then x is actually a convex combination of just two of the vertices. As we saw earlier, convex combinations of 2 points live on the line segment between them. But the line segment between any two vertices of a triangle is part of the triangle, so x is a point on the triangle. So, assume that none of the ti are 0. In order to show that x lies in the triangle, we have to do a little algebraic trick. First, notice that since 1 is equal to t1 plus t2 plus t3, if we rearrange, 1 minus t1 is equal to t2 plus t3. This implies that 1 minus t1 is a sum of positive numbers, which, in particular, means it's not 0. That'll be useful in a second. This identity will also come in handy later, so I'll put it off to the side. The trick is this. We do nothing by both dividing and multiplying the t2v2 plus t3v3 part of the sum by 1 minus t1, which we can do since 1 minus t1 is not 0. This shows that x is a convex combination of these two vectors, v1 and this other, let's call it y. So now we know that x lies on the line segment between v1 and y. So let's take a look at y. It's a scaled sum of v2 and v3. Could it be a convex combination of v2 and v3? That would put it on the line segment between v2 and v3, which would, in turn, imply that x is on the line segment between a vertex, v1, and a point on the boundary, which would mean that x is in the triangle, just as we wanted. So let's check. First, are the coefficients in this sum between 0 and 1? Well, in each case, we're dividing a positive number by 1 minus t1, which, recall, is a positive number. So the coefficients are also positive numbers. Can we show that they're not greater than 1? Well, we're going to want to try to show that they add to 1, and since they're positive, if that's true, then they must both be less than 1, since otherwise they'd add to something greater than 1. So we can actually skip this step, since if the proof works out, this part's automatically true. So let's check if they add to 1. If we add them together, we get this. If we now apply our special little identity from before, it turns out we're dividing a number by itself. So we do get 1, and the proof is complete. So what we've shown is that a triangle is the set of convex combinations of its vertices. We showed earlier that a line segment is the set of convex combinations of its endpoints. What about that other space, the individual point? Well, if you have only one point P, then a convex combination of that point is a sum of scaled copies of P with non-negative coefficients that add to 1. So it's just P. So the set containing just one point P of Rn coincides with the set of all of its convex combinations, since they're all just P again. Having established this, it's time for more terminology. To avoid saying the set of convex combinations and writing it out over and over, let's make another definition. If X is some set of vectors, we'll call the set of convex combinations in X the convex hull of X, written co-X. So, our line segment is the convex hull of the set consisting of its endpoints, the triangle is the convex hull of its vertices, and the point is the convex hull of the set containing just that point. So, why are we using the word convex everywhere all of a sudden? It's because of the following. If we have a set X of vectors, and two convex combinations, x and y, in X, then the line segment between X and Y consists entirely of convex combinations in X. That is, if X and Y are convex combinations in X, then 1 minus Tx plus Ty is again a convex combination in X. So, the convex hull of X, as a set, has the property that you can walk in a straight line from any one of its points to any other without leaving the set, since every point along the way is another element of the set. This property of subsets of Euclidean space is called convexity. Why? Well, a set for which this is not true must have some dents. If walking in a straight line from X to Y can mean walking out of the set, that means there's an indent in your set. A set is convex when this doesn't happen. In a convex set, you can walk along line segments between points and then along line segments between those points and so on as many times as you wish, and you'll never leave the set. The points that you can reach in this way are exactly the convex combinations in X. A nice exercise for the enthusiastic viewer: prove that a set is convex if and only if it is equal to its convex hull. This implies that not only is the convex hull of any set convex, any convex set is the convex hull of some set. So, in the plane, a point is the convex hull of one point, a line segment is the convex hull of two distinct points, and a triangle is the convex hull of 3 points, so long as these points don't lie on a line, since then the triangle collapses to a line. What about the convex hull of 4 points? Well, if we stay in the plane, we get a quadrilateral. If we go up a dimension, however, and take the convex hull of 4 points in R3, then so long as the 4th point doesn't live in the same plane as the first 3, what happens is that we take a triangle and add in all the points on all the line segments walking from points on the triangle to the extra vertex, and we get a filled-in tetrahedron. This is kinda like a 3-dimensional version of a triangle. If we want to go higher to R4, which I cannot draw, and take the convex hull of 5 points, you can imagine that you get a 4-dimensional version of a triangle, so long as those points don't all lie in a common hyperplane. We can do this in as many dimensions as we like, with as many points as we like. If n is any natural number, then so long as we have at least n dimensions, if we take the convex hull of n plus 1 points, which don't all lie in an n minus 1 dimensional hyperplane, we'll call this condition independence for short, we get something we can think of as being an n-dimensional version of a triangle. For this reason, the point and the line segment are sometimes thought of as being 0 and 1-dimensional triangles. These higher, or perhaps lower dimensional triangles are called simplices. The convex hull of n plus 1 independent points in Rm, where m is at least as large as n, is called an n-simplex. Simplices are just little chunks, finite in size, simple in shape, one for every dimension. They capture a piece of space of their chosen dimension in perhaps the simplest possible way, and represent just a bit. These are the simple spaces that we'll use to investigate complicated spaces, many of which are made up of simplices in some way or another. There's one little problem though. In order to build a simplex, you have to choose some points to take the convex hull of. Mathematicians hate making choices. We prefer to have our playthings determined by their intrinsic properties rather than some arbitrary human choice. For our purposes, it would be convenient to have fixed simplices, explicit sets of points, one for each dimension defined as the convex hull of some specific special points. We're in luck because Euclidean space comes with special points. See, a point in Rn is a coordinate vector, a list of numbers. Since some numbers are more special than others, namely 0 and 1, some points in Rn stand out. If we're in n dimensions, there are n points distinguished by the fact that their components are all 0 except for one of which is 1. We call these the standard basis vectors. That is, if I is a natural number between 1 and n, the ith standard basis vector ei is defined to be the vector with zeros everywhere and a 1 in the ith place. So in R2, e1 is 1, 0 and e2 is 0, 1. There's a little bit of an abuse of notation here, since Rn has its own ei for each n, e1 could mean 1, 0 or 1, 0, 0, and so on, depending on which dimension we're talking about, so we really should write something like eni, but in practice, there doesn't tend to be a problem with just writing ei. One of the main reasons to consider these particular points is that a sum of scaled copies of the ei is the vector whose coordinates are exactly the coefficients in the sum. Watch. So, in particular, a vector in Rn is a convex combination of the ei precisely when its components are the coefficients of a convex combination, namely, they're between 0 and 1, and they add to 1. So, definition. The fixed, standardized simplices that we'll use to do our bidding are the so-called standard n simplices, written for each n delta n, defined as the convex hull of the standard basis vectors in Rn+1. Equivalently, the set of coordinate vectors in Rn+1, whose components are non-negative and sum to 1. So, delta 0 is the subset of R1, which contains just the number 1. Delta 1 is the line segment between E1 and E2 in R2. Delta 2 is the triangle in R3 with vertices E1, E2, and E3. Delta 3 lives in R4, which I can't draw, but it looks like a tetrahedron. Our study of homology will be centered around maps from the delta n into other topological spaces, including between the different delta n. To sum up, today we met the Euclidean spaces Rn and some of the methods by which we construct new spaces from Rn. We use this to investigate points, line segments, and triangles, leading to the language of convexity and culminating in the construction of the protagonists of homology, the standard simplices. In the next video, we'll explore some properties of simplices and how they lead, ever so naturally, to homology. I hope to see you there. Big thanks to my patrons. It means the world to me that you'd support my channel financially during these incredibly precedented times of economic and political devastation. Thanks for watching, see you next time.